All right, everybody. Big finish coming. We're talking about doing something called thermodynamic control. Versus kinetic control. Thermodynamic happens when equilibrium happens. It's called thermodynamic equilibrium for a reason. It favors more stable molecules. If you use a limiting amount of LDA, you'll have an anion here and still some unreacted diester. The anion here is a new base that doesn't have the strict stipulations of LDA being so bulky and only to take this H, that's LDA's only job. Now you're getting a second reaction where the alpha anion here that you're about to make, and we'll show it, the mechanism will show the whole story. So you need your LDA, 2 isopropyls on a nitrogen that has 2 lone pairs. I only need 1 for my mechanism. Grab that alpha H. This is all LDA knows how to do. One-way street. This thing, too strong of a base to be equilibrium. CH3O, carbonyl, methyl, C. I know. Hate when he does that. 1, 2 CH2s, 1, 2 CH2s, anion. I don't know if I'm gonna, no. Just made a mess. Wow. Okay, it's gonna make me do this, apparently. For the reaction below, it's the same first step. Take the time. This is not actually for this reaction, it's for the one below. Okay. And what happens if you have a limiting amount of LDA? This base that you made here can react with unreacted version of molecule above. R equals, and grab the H from here. Oh, I won't show it even. Show the H here. And grab it from a second molecule, or even itself, maybe. 1, 2, 3, 4, 5. It can reach the different distance between this carbon and this H is 5. That's perfect. You don't even have to say intermole. Grab the H. And this part is actually 50-50 equilibrium, pretty much. Probably a little more forwards than backwards because of stability. And you're generating CH3O, carbonyl, anion. And then we'll go like this. C, 2, 1, 2, 3, CO2. There you go. And now it's time to do red first, blue second. Get our Claisen going. Yep, directed Claisen condensation coming up. Oh, going with dark blue. Not usually the case. Lone pair on O comes back, kicks off leaving group. And you're going to draw what's right above it. I'll draw it upside down because You say, wait, why are you drawing that when you're done? Great question. Why are you drawing this when you're done? Wait, in fact, in this particular example, we are done. Because normally this OCH3 you generated is a sufficiently strong base to take the alpha H between two carbonyls. And you would have to do that. Why do we not have to do that in this particular example? Normally, that strong base, OCH3 minus, grabs the alpha H that's between the two carbonyls. Why can we not do that here? There is no alpha H between those two carbonyls. This is that molecule above. I don't think it takes a great imagination to see that they are the same molecule. And we don't have to do the deprotonation step followed by HCl, which is the protonation step. So that HCl is actually unnecessary in this case. And what's going on after that? What's going on from here to here with hydroxide and an ester in water, followed by HCl, followed by heat? What is that combination called? The rap song. That's all I wanted to hear, so I can copy my rap song from back here. Here we go. We're rapping poetic here. And yeah. There it is. Fits nicely right there. So let's start our saponification. What's going to happen during saponification? Hydroxide attacks carbonyl of ester. Electrons up, electrons back. Methoxide, bye-bye. And there's your CH3, O minus, plus, HO, bonded to carbonyl, bonded to carbon with methyl, bonded to carbonyl. Did I do that right? Red's here, carbonyl's here. Turned color for some reason. There we go. And that didn't work out at all, did it? Okay, it's a disaster. Sometimes you got to admit when you have a disaster on your hands and just start from scratch. Man. CH2 once, twice, carbonyl. Bond to carbon with methyl. Looks awful. 1, 2, 3, 4. What am I missing? There's 3 CH2s, that's why. You know, sometimes you just get one of those days going. There you go. Looking terrible. Okay. So there you go. You got this OH here. Why did I have to draw that bond? We're not done. You can't. You want to start with a decarboxylation? You can't, because this combination has to react with itself first. Acid base, strong base, carboxylic acid. There you go. Saponification's over when you're at the carboxylate stage. And that's where you're at. You're at the carboxylate stage. That's saponification. So I guess you could just try to summarize by saying 1 and 1 are now done. Time for 2 for the acidification and then heat for the decarboxylation. Let's roll. HCl. Whoa. And let's draw this carefully. You got your cyclopentane. You got your methyl. I'm going to draw the carbonyl sticking that way, and the O and the H sticking that way, right there. Because it's time for decarboxylation. I don't think I need that lone pair either. Doesn't go that way. Pi grabs H. Sigma becomes pi. CO2 is liberated. CO2 is liberated. You have a molecule that looks like this. And I'm going to do a flip on it. I hope you guys don't flip out on me. I wanted it to look a lot like this. Oh, and that's not it either. My goodness. That's an OH down there. Yeah. Oh, I didn't do a good job at all. Hope you didn't get that far. I didn't do a good job. Why don't I just draw what I see? That was my whole problem there. And for having trouble seeing stuff here, carbon 1, 2, 3, 4, 5 is 1 is going to be the carbonyl, 2's got the methyl. I'm making an enol into a ketone. What's that? Uh-oh. I'm making an enol into a ketone. What's that process? Oh. If you look at all the videos, there's some videos where I would count for an answer to that question. And if I got to 2 seconds, I got upset. I think we're on 15 seconds now. I'm making an enol into a ketone. What's that called? Oh, this is going to be, we're going to have a nice video with a gap in it. Maybe I'll do a little dancing over here. Yeah, I can't dance, I'm sorry. Sorry, say it again. Tautomerization. I didn't even get my coffee. All right. So now, tautomerization can be of the intramolecular variety when there's no acid or base present, or it can be acid catalyzed, or it can be base catalyzed. Which of those 3 must this be? You must look at the things available in step 2, and don't tell me there's no base or acid available. When you see HCl, do you think base or acid? Which one? This is the acid catalyzed version of tautomerization. Right now, do it. Acid provides H for the alpha position. Base grabs H from the enol. Here we go. Cl minus grabs H. Sigma becomes pi. Pi picks up a proton. It does look like a classic elimination set of arrows too, doesn't it? Yeah. And that's it. Tautomerization. Save. Okay. Nice. A lot going on in this one. Computer thinks so too. It's taking time to save. We're going to be picking up the next one from the kinetic control down here when it lets me. There we go, finally. So, in this one, you're allowed to do this if you've already shown how it happens. See above. We took the H off up here to make this, which is the same as this. I hope that's clear. Now, under kinetic control, this is the only thing that happened. You had so much base that 100% of these reacted and made 100% of those. No equilibrium's happening now. This is the end of the story. Equilibrium's been shut down. And this thing's going to do an attack on the carbonyl over here. Okay. And what's going to happen there? We're going to make a ring. Let's try to make it like what we started with over here. CO2, CH3 on the right, comes down to here, sigma, 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 sigma. That's going to be 6. I don't like it. There. Nice. Oh, and the electrons come back. And I'm really sad now because I don't even know if I can do this without a mess. Yeah, crossing arrows. Wow, that's definitely not, that's not cool. Some surgical eraser coming. If I show this on the left, right side, there we go. That lone pair disappeared, but it's back. It comes back and kicks off the leaving group. Classic Claisen. And we got a carbonyl up there. And where's that methyl? It's past the carbonyl. There you go. Having trouble seeing this? Pink. Methyl, 2, 3, 4, 5, 6. Very good. All right. Now you think you're done, right? Here's one where you're not done. Unlike our previous example, this OCH3 minus you generated can take this H. Why? Because that H has a very special pKa. 10. Between two carbonyls. So you've generated the conjugate base of the product above. And it looks like this. Terrible double bond. And where's it going to pick up a proton from to get to there? Step 2, HCl. There you go. That's a more normal Claisen outcome. There you go. And look at that. Right after I put that H back on, step 1. What's going to happen? Base undoes what the acid just did. Generates a new anion, a very special anion. An anion that, if it has a choice, can undergo 1,4 addition. Wow, 1,4 addition. It's big on our test. I don't even know how to do this. Here we go. Here we go. Still too big. Yeah. Coming down here. You have generated this species here. Why pink? I don't know. Methyl, CH2, CH2. CO2, CH3. And the anion is right there. And that anion can attack the carbonyl of this aldehyde. Why is that a bad idea? We've had anions attack carbonyl. It's all chapter. Why is it a bad idea here? Look at the product. We've got this species here. No, don't go away there. A, B, C. The carbonyl is still a carbonyl. The B still has a methyl. C got attacked. I hope it's clear. C got attacked. There's a new bond between the ring and C. Please attack C. It's called 1,4 addition. This arrow here is 1,4 addition. It generates an enolate. Wow. Generates an enolate with a new bond here to the CH2, which goes to a C with a methyl, double bond O minus. There you go. You want your ABC on there? A was the aldehyde, B, C. Enolates are the conjugate base of aldehydes and ketones. We need some kind of an acid to protonate it. Ethanol, perfectly good acid. Ethanol. Resonate, protonate, and celebrate, because you're done. There you go. Save. Big picture. Well, save takes for what? Forever now. Yeah, sorry about that. Whoa. Saves there. That's good. Maybe a little small, but all right, guys, stop on the video. Oh, that's